So where to begin? Let's start with a circle. A circle of radius r is described with an equation. If this is the, let's say this is the x direction and this is the y direction, then it would be described according to the equation x squared plus y squared equals r squared. Another way of describing, if we wanted a point up here on the circle, you may describe that point as x comma y, but you can also describe it as r cosine theta comma r sine theta, and that has the form, so that equation becomes r squared cosine squared theta plus r squared sine squared theta equals r squared. You can cancel out all of the r squareds and you end up with cosine squared theta plus sine squared theta equals 1. Okay, similarly, we can do that with some hyperbolas. The hyperbolas have a couple of asymptotes along, say, x equals y and x equals negative y. And actually, yeah, that's fine. Say we pick these two hyperbolas, and what these points have in common is that, okay, you go over and you got x squared minus y squared equals, and we'll call this distance r, equals r squared. And that will be the same for all of these. It's not really a radius, but it's just the distance, the closest distance that hyperbola gets to that point in the middle. With this, we can replace the equation with, we can replace this point here with r cosh phi, I'm going to call it phi, and r sinh phi. And this becomes r squared cosh squared phi minus r squared sinh squared phi equals r squared, or simply cosh squared phi minus sinh squared phi equals 1. Sorry. Now you can do the same thing with these two hyperbolas, with r being this distance, but in that case it's y squared minus x squared equals r squared. Okay, now let's talk about trigonometric and hyperbolic rotations. A counterclockwise rotation, can be represented by this formula here. X prime, y prime equals cos theta, negative sine theta, and cos theta times x and y. And this is a matrix multiplication. So it's cosine theta times x, the new x prime, after you rotate it an angle of theta degrees counterclockwise, the new x prime will be equal to the cosine of that angle times x minus the sine of that angle times y. And the new y prime will be the sine of theta times x plus the cosine of theta times y. I'm going to write this in a little bit different way. Let's write this with a right triangle in mind. And cosine theta is equal to x over r, which is in turn, but I want to express r as in terms of x squared and y squared, so that is x over square root of x squared plus y squared. Pythagorean theorem there. And then I'm going to divide by x over x, so I'll have 1 over square root of 1 plus y squared, y over x squared. So y over x squared. Okay, so cosine theta is 1 over square root of 1 plus, so I'll rewrite that. 1 over square root of 1 plus y over x squared. And this is sine theta. Sine theta will be y over square root of x squared plus y squared. But I still want it in terms of y over x. So I'm going to actually put equals y over x divided by square root of 1 plus y over x squared. So, and I'm just going to refer, you know what, instead of y over x, I'm just going to call that m. I'm going to call that the slope. M is the slope y over x. So this is 1 over the square root of 1 plus m squared, and then negative 1 or negative m over square root of 1 plus m squared, negative or positive m over square root of 1 plus m squared, and then 1 over square root of 1 plus m squared. So that is the rotation transformation in terms of the slope instead of in terms of the angle, theta. Okay, now I'm going to go out to the internets and find on Wikipedia the Lorentz transformation function, and it says t prime equals gamma t vx over c squared, and x prime equals gamma x minus vt. I'm going to write those things down, and furthermore I'm going to find out the definition of gamma is this thing right here, square root of 1 minus v squared over c squared to the negative 1. So I've got this all written down, and so what I'm going to do is I'm going to get this in that form, t prime and, well, actually first, you know what I'm going to do? I'm going to multiply this by c. So I'm going to write ct prime equals gamma ct plus vx over c. Okay, so I multiplied everything by c. So this is just, and then can I do the same thing with this one? I do want a c in there, so I'm gonna actually do something with this one where I take that minus, I'm gonna make this v over c times ct. So I divide by c and multiply by c at the same time. Okay, and then I'm going to write this in a matrix form where I say ct prime and x prime equals, and then I'm going to put ct and x over here. So ct prime is gamma times ct, so I'll put that gamma right there. And plus what times x? V over c times x. V over c times x. Then I've got this x prime is equal to gamma times x, so I'll put the gamma right here, and negative gamma v over c times ct. Negative gamma v over c times ct. There is something wrong. I want a negative sign here. Okay, good. I just miscopied. There's some minus sign there. There should be a minus sign there. And there also, I did not multiply through the gamma there, so there should be a gamma here. Good. Okay, that's exactly what I want. And a negative sign there. Good. That's what I'm familiar with. What I'm going to do is now is v over c. I'm going to just call that, it's a proportion of the speed of light. I'm going to name that variable beta. So this is gamma, negative beta gamma, negative beta gamma, and gamma. And then I'll have CT and X. Okay, this is one of the ways I have it memorized, and then we'll check that this gamma is 1 over 1 minus beta squared. So this is equal to 1 over square root of 1 minus beta squared and negative 1 over square root of 1 minus beta squared. Okay, beta, negative beta over square root of 1 minus beta squared. And then this one is negative beta over square root of 1 minus beta squared. And this is 1 over square root of 1 minus beta squared. Okay, so let's go ahead and compare that. We have 12. Notice the similarities between this equation and the one we derived for rotation. We've got 1 over the square root of 1 plus m squared, negative m over 1 plus m squared. All the m's are basically, all the positive m squareds are basically negative b squareds, beta squareds. Also, if you use phi is equal to the arctangent of beta, the same as this one is m is equal to the arctan of y over x. This is arctangent of v over c. Then you can write this as cosh phi, negative sinh phi, whoops, negative sinh phi, negative sinh phi, cosh phi. And this is a boost to the right, I think. This is if you do a boost to the right, it kind of shifts everything to the left, just as if you rotate, if I rotate the page clockwise, the coordinates change counterclockwise. If you want to do a shift to the opposite direction, everything, you would either plug in negative phi in here, or you would switch those negative cinches to positive cinches. So a big difference between the trigonometric rotations and hyperbolic rotations is when you do one of these counterclockwise rotations, this remains a rigid structure as it turns around. But with the Lorentz transformation, this it smashes. It smashes in this way and in this way and comes out this way and out this way, as everything kind of curves around that way, curves around that way, curves around that way, and curves up this way. So it stays on those hyperbolic paths, or so that events that are on the hyperbolic path stay on the hyperbolic paths, and but it's not a rigid structure, but it does preserve these slopes. These slopes are preserved as things change as it changes its shape. Another thing to point out is that there is no limitation on where this operation takes place. Okay, you might think, okay, under the rotation transformation, your situation is, okay, I'm going to take an object and spin it around the axis. Okay, and therefore the domain of the function and the range of the function is that object that you're rotating. Well, that's fine, but also, what if you are not rotating an object, but you're rotating yourself? You didn't just change the didn't just change the domain and range of that object. You changed the domain and range of every event throughout the space-time. You basically changed your perspective, your point of view on all of the events in space-time. The same thing, though, happens with the Lorentz transformation. You could just consider a single object that you accelerate, and that object gets Lorentz contracted and whatever. I can't do what I just did with this camera to show you the Lorentz transformation. The best I could do is make a simulation of something happening, but um, but I think there's a simulation out there called A Slower Speed of Light, done by MIT Labs several years ago, that was pretty good. But for this thing, I can't show you what it would look like if I accelerated the camera a significant portion of the speed of light. But what would happen is essentially that what you would see is the objects that are in front of you would be spaced out more. It's hard to. I think I did this better in an earlier video, but the things in front of you would get spaced out more, and the things behind you would get spaced out less, based on what you could observe along that speed of light line. And of course, I am drawing somewhere where the camera can't see. But you should. But this function, the Lorentz transformation, doesn't have a limited domain and range. When the point of view of the observer changes, it affects his perception of the coordinates of every event in the space-time. Just as when I change the angle of the camera, it changes the coordinates of every point in the space. Okay, so that is, I guess I have nothing more to say for now.